Hi, this is my video number 6. Number 6, I'll talk on the sequence of area numbers. Sequences of area numbers. Okay, so first, of course, I will give you some introduction on what is sequence. I believe this is a new topic for you. So I'll try to make you a strong fundamental for the beginning, to introduce you what is the sequence is all about and what is the main point that we are going to discuss in the sequence, so that you get the general idea what we are going to discuss in the couple of lectures, in the next couple of lectures. So the sequence, basically we written in the definite order. So like we have U1, U2, U3 and so on, UN and so on. Okay, of course this is the first term, this is the second term, and so on. We have up to n terms. So here is number of terms. Here we have 1, 2, 3, 4, 5 and so on. We don't have like term number 1.1, 1.2. we don't have that. We have a definite number 1, 2, 3, 4, 5. So this is the term. And the for the infinite sequence, this is, we call it infinite sequence. We denote as so let me write this. This is the first term, okay, of the first term. Oh, should be small t there. First term, we have second terms and so on. Now for the infinite sequence, we denote as like that. Just a curly bracket with elements, say V1, U2, UN. That's the way we write the sequence. Or in short, we can denote this. We can denote this as just that UN. This means it is a sequence. Or can also write UN n from 1 to infinity. But normally we just write this without the limit point, because we know when we say infinite sequence, so which means we have terms U1, U2, U3, UN and so on up to there's no limit basically. So in terms of the meaning of this is basically U1, U2 and so on. Alright, so that's a sequence. Alright, so what is the example? I give you the couple of example and explain what happened to that example. Okay, so let's see a couple of example of sequence. For example, if you have that sequence, so if you list down this sequence, what we have, n begin from 1, so you can see this is 1, 3, 5, 7 and so on. We have 2n, this is the n terms and so on. Okay, so let's consider this as the first example here. The second example is that if I have 1 over n. So for this sequence here, we have 1 over 2, 1 over 3 and so on, 1 over n. That. Okay, and the next example, we can think of like cert n minus 3. And this is also sequence where the first term is 0, n from 3 to infinity. So the first term is 0, the second term we have 1, cert 2, and cert 3, and cert n minus 3, to the n terms, and so on. Okay, now if you look at this term one by one, so for example, sequence number 1 here, A, sequence A. So if you want to sketch those in terms of to visualize this much clearly, so we have 1, this is our n, right? So n is 1, 2, 3, and so on. So as you can see from that, when n equal to this is our un. Alright, so when n equal to 1, so we have 1 here. When n equal to 2, we have 3. This is the second terms, 3. And then it goes to 5, 5, and so on. Just goes to like that. So what you can see from this example is that this sequence, the bigger the n, the bigger the sequence. The bigger the n, the bigger the terms in the sequence. So as you can see here, when n equal to 1, 1 equal to 2, we got 3, 5, 7, and so on and so forth. So it's getting bigger and bigger and bigger. So what we can say here is that this sequence is increasing. This sequence is increasing, and the behavior of this is that apart from its increase, it's increased without bound, without bound. So what does it mean? Increase without bound. It means that it's increased without any limits. It's keep on increase, keep on increase, keep on increase as long as n getting bigger and bigger, as long as we increase the n. Okay, so we can see from here that as n getting bigger and bigger, and this sequence here that un are represented as 2n minus 1, that also goes to infinity. So this case we call it as a increasing without bound, or in short we can say unbounded sequence. Unbounded sequence. Unbounded sequence. So that's the first example. The second example is that, look at B there. Look at B there. So we might have, for that we can see, if we can plot this or sketch that. So we have maximum is 1. So let me put a little bit bigger there. So let's say 1 here. When n equal to 1, so we have 1 there. When n equal to 2, we got half. When n equal to 3, we got 1/3. There's half, 1/3 somewhere here. When 4, 1/4, and so on. Okay, so what you can see here is that this sequence getting smaller and smaller and smaller and smaller and smaller, but it will not cross the line y0, or the sequence will not be 0. As you can see from that sequence, you can see from there, no matter how big n you choose, no matter how big n you choose, this sequence will not go to 0. It approaches 0, but not 0. Even if you choose n 10, for example, it's still not 0. Even if you choose n thousand, it's still not 0. If you choose n million, it's still not 0, but very close to 0. So what you can see here is getting closer and closer and closer to 0, just like that. Now notice that here I use a cross here without a line, without a line, because remember that sequence, term of sequence, we count as 1, 2, 3, 4, 5. We don't have 1.1, 1.2, 1.11, and so on and so forth. So that's why we only put cross. So do not when you write a sequence or plot a sequence, don't do this. Yeah, this is for a graph, whereas a sequence is not that way. Okay, so in this case, we say this sequence is decreasing. Yeah, decreasing. And if you can see the bigger the n, the smaller the sequence, the element of the sequence is getting smaller and smaller and smaller, and later on it approaches 0. Yeah, very close to 0 but not 0. So decreasing, and we say approaches its limit, which is 0. So in this case, we say the sequence is bounded below. Yeah, the sequence is bounded below. Oh, that. Okay, what about number 3 here? The third example. So for the third example here, you can see again, when n increase, we have 0, 1, square root 2, square root 3, square root 4, square root 5, and so on and so forth. It's getting bigger and bigger and bigger. Again, in this case, the sequence increase without bound. Do we only have these two situations? No. We also have other example. Let me give you. Just I give you in term of sketch or graph of that. Say for example, if you have a sequence like we have like this. Yeah. Okay, so this kind of sequence, yeah, this kind of sequence, we say that this is a increase and bounded. Increase and bounded. Okay, so take note that in this introductory parts, yeah, what I have explained, that I give you what is the sequence, okay, and what the main point in the sequence is that, or the main word that involved in this sequence, that we have increasing sequence, bounded or unbounded, so increasing or decreasing, we have bounded or unbounded, unbounded. So that's what I have, the terms that I introduced to you at the moment. Alright, so we have either increasing without bound, so it means it keep on increasing and keep increasing, or increasing with, or increasing but approaches, increasing and approaches to certain limits, a certain number. So that in case we say increase and approach a limit, its limit. The same thing with decreasing. We have either decreasing without bound or decreasing approaching the limit. So which means in that case the sequence is decrease and bounded, increase and bounded. Okay, so we have those terms. Now let's come back to this example here. Now for this case, when it's increased without bound, we also say that this sequence un is divergence. Okay, so that's the third terms I introduced to you. We have increase, decrease, with bound, unbounded, and next, if we increase without bound, we call it as the sequence is divergence. Whereas for this case is decrease or increase, increase or increase. So we have the sequence un either increase or decrease, but at the same time approaches limit and approaches its limits. So we call this sequence as a convergence sequence. Convergent sequence. So for the rest of the lecture for this topic, we only deal with increasing or decreasing sequence, bounded or unbounded sequence, divergence or convergence sequence. Alright. Of course, from there we will develop a theorem, prove some theorem as well. Now, look at the example. I told you that we have increasing, decreasing sequence. But what about this example here? Consider another example. What if you have this kind of sequence? N equal to 1 to infinity. So this sequence, if you list down the terms by terms or element of that sequence, we have minus 1, 1, minus 1, and so on. So in this case, if you plot that, so we have 1, 2, 3, 4, 5, and so on. So we have for 1, we have negative 1. Let's say negative 1 is here. We have 1 is here. So negative 1, we have 1. We have negative 1. We have 1. Next, negative 1. And so on. Okay. So it is obvious in this case that this sequence will not exceed or bigger than 1. The element of that sequence not bigger than 1, not lesser or smaller than minus 1. So in this case, this sequence bounded. But as n increase, you look at this, as n increase, this sequence is not approaching its limit. Okay, it's not approaching its limit. So in this case, we say bounded, but the sequence is not converged. So we have bounded, but not converged. So other terms we call it as a oscillate. The sequence oscillate between minus 1 and 1. Other term we call it as a oscillate. Okay, so for other example of this kind of sequence, we can see like a cos or sine. Like other example, like if you have a sequence of cos n pi over 2, this is also bounded but not converged. Yeah, this is also bounded but not converged. Then there is a question arise: does or do all the oscillate sequence does not converge? Okay, so I just asking this question: do all the oscillate sequence do all the oscillate sequence not converge? This is a question. The answer is no. Why? So look at this. Yeah, I don't have the specific example right now. There are many, of course. So for example, like if you have a sequence like this, between 1 and getting here is 1, say this is -1, and we have that half in between. So for example, if you have this that, and next here getting smaller and smaller and smaller, and so on. So it's oscillate, yeah, positive, negative, positive, negative, positive, negative, but it's getting smaller and smaller and smaller and smaller, and later on approaches its limit 0. Yeah. Example for this, maybe you might think of like we have a sequence like minus 1 over n to the this kind of a sequence to the n. You can have this. So in this case we have -1 when n equal to 1, you got -1, and again half. Yeah, for this case you have from that you get that and that and that and that, and get smaller and smaller. So it's converged to its limit, which is 0. Okay. What about this sequence? -1 n plus 1 over n. Does this sequence converge or diverge, increase or decrease? Yeah. So let me put the question here: does this sequence decrease or increase? Yeah, bounded or unbounded, and converge or diverge? Converge or diverge? I put the question mark there. So this so how to determine this at the moment? Yeah, at the moment, the best thing probably you can try to list down each of those elements. So when n equal to 1, so we have 1, right? N equal to 2, we have minus 1 over 2, and then we have 1 over 3, and then we have 1 over 4, and so on. Up to n terms, we have minus 1 n plus 1 over n, and so on. Okay, if you list down each of those elements of that sequence and try to plot this, I don't give any proof for the moment, just sketching to give you the idea, as I told you at the beginning, that this is just introduction of the sequence. So I just want you to get this, the idea, what is the sequence, what is the bounded, unbounded, what is decrease, increase, what is convergence and divergence. So that's the main point of the talk right now. All right, so if you list down this thing, okay, and try to plot those. So what we have here, we have 1 is here, let's say -1 is here, then we have -half, then we have half there, and then we have 1/3, and so on and so forth. So then when n equal to 1, we have 1 is here, say this is 1, next is half, next is 1/3 here, next is -1/4, and so on. So you can see here, it oscillates. Okay, for the n even terms is decrease. For odd term is increase. For the even terms is increase. Okay, so other word we can say it is oscillates and converge to a certain limit. So in this case, the sequence is bounded and convergence. Bounded and convergence. Now, let me discuss a little bit further on the boundedness of the sequence. The boundedness of the sequence. I hope up to now you have an idea when we say about sequence. So what is the main subject that we are looking for? Yeah, we have, let me repeat that again. So we have decrease, increase, bounded, unbounded, converge, and diverge sequence. All right. Now we go a little bit more detail on the boundedness of the sequence. Boundedness of the sequence, or we say bounded sequence. Bounded sequence. So now we have a definition. We have a definition that the sequence, this un, we say is bounded if there exists a positive number, yeah, if there exists a positive number m such that absolute of un less than or equal to that number m for all n, yeah, for all n. This symbol is stand for all n. Now, of course, all n here, I mean n equal to 1, 2, 3, 4, 5, and so on. Just a integer number, positive integer. So mathematically, what we say? We say un bounded. If there exists, or we can find a positive number m such that un less than m. Okay, so in future, if we write un less than m, so this means that un is bounded. So in this case, if I write like this, in the future means un is bounded. Those sequence is bounded. Now, let's look at an example of this. Example. Consider this sequence 1/2n. Okay, so if you take the absolute of those terms, we have 1/2 to n. Of course, this is less than some number. What? Less than 1, right? When n equal to 1, you got 1/2. When n equal to 2, you got 1/4, and so on. So the biggest, if I put less than 1, this is true. So in this case, our m is 1. So this is our m. So if you look at again the definition is that we say un bounded if we can find a positive number m. So in this case, we can find the positive number m. So therefore, in that case, the sequence 1/2n, this is bounded. Okay. What about other sequence? Let's say the one that I gave in the beginning. We have a let's say okay, let's say this sequence n plus 1. Yeah, this is example number 1. Example number 2, if you take this minus 1 n plus 1, so since the sequence itself oscillate between minus 1 and 1, so it's not going bigger than 1 and lesser than negative 1. So again, this sequence less than m, or equal to less than 1. So in this case, our m is 1. So again, this sequence is bounded. So we have this sequence is bounded. Okay, let me give something a bit different. What about this sequence? We have n squared plus 6 over n cubed plus 1. Does this sequence bounded? That's question. Okay, let's do it. So the purpose is to find integer m. To find a number m, not necessarily integer. To find the number m, positive number m. So that's the purpose. So from there, how can we find those n? So if you look at those, it's look like what? Here n squared over n cubed. N squared over n cubed. But if you look at the numerator, we have plus 6 is getting, well, it's increased quite big, and this one is n to the cube, also increase much faster as compared to this. Of course, I mean increase faster means when we increase n, so n cube getting bigger much faster than n square. Of course, when n equal to 1, you got this one 1. When n equal to 2, you got 4. N equal to 3, you got 4, 9, right? and this I don't say meaningless, but the contribution from this part is quite small as compared to n itself. Now, whereas for n cube we have n, we have 1, we have 9, 27, 81, so it's getting faster, increase much faster. But how to find those bound if there exists? So now look at the absolute of those terms. We have n squared plus n over n cubed plus 1. Now, one thing that I want you to aware of, where you know this thing, if you have a over b, if you increase a, then definitely the terms that you increase much bigger than the previous one. So what I mean is that this term here, if I increase a, let's say by 1, and we stick b, okay, then definitely in this case a plus 1 over b is bigger than a over b. And we can keep on doing this, a plus 2 over b, and so on. We can do that. Okay, so this example of how to keep the right hand side always bigger than the left hand side. So the right hand side always bigger than left hand side, right hand side always bigger than left hand side. Also, you can decrease the denominator. Decrease the denominator. So for example, if I have a over b, if I put a over b minus 1, then definitely in this case the right hand side is bigger than left hand side. Then you can keep doing this, a b minus 2, and so on. So what we can see from here again, the right hand side always bigger than the left hand side. So we use this idea for this problem here. Okay, now remember that we want to find, remember that for the boundedness we want to find a number n such that un less than those number m, either less than or equal to. Okay, so how to do this? First, of course, if I use the second one here, I can decrease denominator. So what we have, this will be, because n is always positive, this part is always positive, n is always positive, so all term numerator as well as denominator is always positive. So I can always just write this as n squared plus 6 over n cubed plus 1 without the absolute symbol. Then of course from here, if I decrease the denominator like that, so what we have, this is less than n squared plus 6 over n cubed. This is true. Okay, this statement is true based on this. Now I can again increase the numerator. I can increase the numerator. So if increase the numerator, I have n squared plus 7 over n cubed. This is true. Correct? So logically correct, so it means mathematically is correct. Mathematics is easy, right? As long as you can think it's logic, then it's correct. Now, you can keep on increasing those numerator. You can have n squared plus 8 over n cubed. And again, this is true. And you can keep on doing this. You can keep on doing this until you have n squared plus n over n cubed. It's still true, but you cannot do anything right now. You cannot do any cancellation. You still cannot find what m is. Remember that m is a positive number, free of n. So that's we are looking to. We are looking now. M is a positive number that free of n. So now if I keep on increasing this, I can goes up to n squared plus, you can see here, I can keep on doing this, n squared plus n plus 1 over n cubed, n plus 2 plus 3 plus 4, and then up to plus 2n over n cubed, and 2n plus 1, 2n plus 3, 2n plus 4, and then next I can get up to n squared plus 3n, 4n, 5n, and later on up to n squared plus n squared over n cubed. And from there, we have 2n squared over n cubed. Okay, of course, in this case, you can keep on increase those numerator until you get n cubed over n cubed. Or from there, you can have this is equal to 2 over n. Of course, for this case, when n equal to 1, you can see obviously this is less than 2. For n greater than, or equal to 3. I can see, yep, for n greater than 2. Okay. Yeah, for n greater than 2. So n equal to 2, we got 2 over 3 less than 2, 4 less than 2, 5 less than 2, then everything. So in this case, this is our m. So it's a bounded sequence. So therefore that sequence is bounded. Another example, many examples here. Hopefully you can understand. What about this sequence here? 1 over 2 plus 1 over 2 squared plus 1 over 2 cube plus 1 over 2n. This is a sequence. If you list down that sequence, what does it look like? When n equal to 1, so you will have 1 over 2. That's the sequence. When n equal to 2, so you have 1 over 2 plus 1 over 2 squared. When n equal to 3, you have 1 over 2 plus 1 over 2 squared plus 1 over 2, 3, and so on. The last term, the n terms, you have this, yeah, 1 over 2 plus 1 over 2 squared plus 1 over 2n, and so on. So that's your sequence. Now, again, the question is, does this sequence bounded? Now, by looking at this, it is obvious that you have a kind of series that I can write as Sn equal to, we have half plus 1 over 2 plus 1 over 2, 3 plus 2n, because we have summation up to n terms. And if you recognize this is just like a plus ar plus ar squared plus ar and plus 1 and so on. So in this case, you can just use the geometric series. Is give you the geometric series. This is a 1 minus r n plus 1 over 1 minus r. Alright, so you can where A is your first term, which is half. Your R is the common ratio between all those things, which is half, and then so on. So you got, for this, you have, if you do those, you have sum of that 1 over 2, and then 1 minus 1 over 2 to the n, or you can make it n plus 1. That give not big difference. And then 1 minus r, we have 1 minus 1 over 2. Then you have, from there you can have, this is 1 minus 1 over 2 to the n, which is less than 1. 1 minus something less than 1. So this is your m. So therefore that sequence bounded. Okay. What about the sequence that we define iteratively? For example, if you have this sequence u1 defined as 0 and un is given as 2 plus un minus 1 for n greater than equal to 2. First thing, can you list down this sequence? List down that sequence. You have, this is 0. When n equal to 1, this is u0. u0 is n equal to 2. Okay. When n equal to 1, when n equal to 2, so 2 plus u1 is 0, so you got cert 2. Next you got cert 2 plus cert 2. Next you got 2 plus 2 plus 2, and so on. So that's your sequence. That's your sequence. Now, how to find the bound for this sequence? So I think the proof of this is not as easy as the previous one, but you can still, because I believe you know what is the, if I say mathematical induction, you know what mathematical induction is. So by observation, of course, this less than 2, right? Definitely less than 2, because square root 2 is always less than 2. So I can say by observation you have by observation we have un less than 2, but that's not the proof. That's not enough to prove that that sequence is bounded. So then you can say, then for n equal to 1, then we have u1, which is 0, which is less than 2. So this is true. Alright? Then we can assume that it is true for n equal to n, or if you don't want to confuse, you can take n equal to k. You can. All right. So if n equal to n, then what we have in this case, un less than 2. This is true because we assume it true. Next, we show it is also true. Next, we show that it is also true for n equal to n plus 1. Okay, and for this part here, I leave it to you as an exercise. Of course, there are some activity that you can think of in the in your notes. All right. So, but for the first lecture on the sequence, which is new topic to you, I think I have given enough background to introduce you what the sequence is all about. The main part is that we have increasing and decreasing sequence, bounded and unbounded sequence, convergence and divergent sequence. Okay, so that's as a to conclude what I have talked just within about an hour. So I stop here for this video. Bye.